Hello everyone, welcome to CPE 517-WS Digital and Computer System Architecture. This is lecture 5, part 1, memory backgrounds. The entire lecture of lecture 5 is about memory. So the first part is memory background. First, some logistics. For this class, some of the slides will be adopted from textbook slides and other researchers such as David Patterson, Sen, CMUS Virtual Machine 2020, Howie, and some videos from YouTube. All the credits goes to original authors and all the errors are mine. Reordering and modifications might be made due to requirements. Okay, so why we talk about memory? The biggest problem here is the processor is important. Well, the memory is lagging behind. When we do computation, we say we have opcode and operand, right? So execution, the operand is fast, which is doing by processor. Well, giving you operand or preparing the operand for calculation is memory operations. So we cannot prepare the operand for calculation. If we only have this opcode, it wouldn't work. We have to stall or waiting until this operand is slowly being provided, right? So that's why memory is important, or data is important, or big data is important. So showing this figure from left to right, we see the gap between the processor performance versus the memory performance is increasingly getting larger. Until 2010, we see the difference is more than 1,000 times. That's a lot of difference. So that's why we introduce cache and different caching strategies try to mitigate this gap. Okay. But before we talk to cache, let's first get some backgrounds about main memory. So the performance of main memory mainly focus on two things. First is latency. Latency concerns about two types of latencies. First is access time, the time between request and word arrives. So we send a request and then the request was responded. Okay. The cycle time is between requests. Okay. Bandwidth is giving a time the total number of data that was served, right? Main memory is typically made by DRAM. DRAM is dynamic random access memory. Here, dynamic random access memory. It contains one transistor and one capacitor. This transistor is gating transistor. It's dynamic since we need to refresh every main memory cell periodically, like every 8 milliseconds, or right now shorter, right? Addresses are divided into two halves, one's a row, one's column. We treat memory as a two-dimensional matrix. There's row access strobe and column access strobe. Well, the fast memory that's cache uses SRAM or static random access memory. So comparing SRAM and DRAM, you see SRAM is static while DRAM is dynamic. So that means we don't need to refresh, and it contains 6 transistors. DRAM is denser but takes longer time to access. So these are two of those memory cells. One's DRAM memory cell, second is SRAM memory cell. That's how it works. So the word line is the switch. Like if it's like the passing transistor is here, right? So if we give some power here, it will allow this line to be connected. Then whatever was recorded in the capacitor can be passed to the bit line, which we can read the data, and then we have the amplifier here to make the power even stronger, so we can easily decide what is the power. And then this side is connected to the ground, right? So because whenever, see here, whenever we read something, it essentially means the capacitor has released the power. Once the power is released, then we have to refresh it. Even we didn't read it because the capacitor gonna leak some power according to the DRAM design. So we always have to, you know, recharge it. That's why we have the DRAM as refreshing required. Okay. Now let's go to the second part. The second part is the SRAM. Okay. Sorry. SRAM has the feedback loop of two NOR gates here. For instance, let's say we have a 0 here, and then NOR gates gets 1, right? 0 passing NOR gates goes to 1, and 1 passing through NOR gates go to 0. So it's a feedback. It's always, if you have some value here, it's always back and forth. So it's re-strengthening the information. That's why SRAM typically does not need refreshing to maintain the value, right? So when it goes to reading the data, it's the same. Okay, let me change the color here. So there's one passing transistor. Another one also has another passing transistor. So we read two values. We have two sides of readings. The first is once you have a word line here coming, sorry, here, word line here, then the passing transistor is gonna be toggled on or latched, and then the BL or the bit line and the NOR bit line gonna read the value. The bit line gonna read the essential value, and the NOR bit line will not read the essential value. So that's typically how it works. Okay. When it goes to the real case, we have like a lot of those memory cells packed in a two-dimensional matrix. Okay. Each one is one memory cell. And then we have the row access strobe and column access strobe to decide which column, which row to access. Okay. So DRAM performance, we have three major, like a very well-known technology enhancements. First is fast page mode, add timing signals that allow repeated access to row buffer without another row access time. It's very straightforward as what we show in the prior page or slide. When you access the word line gonna trigger, the entire row to be read. So in that sense, if you read the data of the same row, whatever you retrieved before can be still buffered. So that's using row buffer. Okay. And the synchronous DRAM add a clock signal to DRAM interface so that transfer will not bear overhead to synchronizing the clock with DRAM controller. Double data rate DDR SDRAM transfer data on both the rising and the falling edge of a DRAM timing. Clock signal doubling the peak data rate. So basically, when the timing is rising, we trigger the read, and dropping is decreasing, we also increase trigger the data rate. So that's why we do double data rate. Okay. Error correction. The motivation is that failures will happen, right? As DRAM cells shrink, it's gonna be more vulnerable. Went through period in which failure rates was low enough that without error correction, that people does not really experience like a lot of errors. DRAM banks are too large now, and servers always correct memory systems. So basic idea is we need to add redundancies. For instance, 0, 0, 1, 0. So if we have add a parity bit of 1 here, when we receive the value of 5 values, we see it's an odd number. It means we at least have a bit flip, right? Because when we add parity value, we always make sure the entire bit stream is an even number. Okay. So that's what we call single bit error correction. There are also 2 bits error correction, etc. So many ways. But when you add, typically what we do is every 8 bits, we have 1 error correction. So that is like 1/8 of the overhead, right? Both reading the data as well as storing the data. And then we also talk about how to use how many bits to represent how many addresses. Please refer to the video of the campus called address encoder, which is 4 minutes, to understand how to do address encoding and decoding. All right.
A decoder, or to be more precise, a binary decoder, is an electronic component that takes multiple inputs and uses them to activate one of many possible outputs. This decoder uses 3 inputs to select one of 8 possible outputs. It's therefore known as a 3 to 8 decoder. If, for example, all 3 inputs are set to a low voltage, the top output line is set to a high voltage. The top output line is activated. If the first input is high, the second output is activated instead. If the second input only is high, so the inputs collectively represent the denary value 2, the third output is activated. If the inputs collectively represent the denary value 3, the fourth output is activated. An input of denary 4 activates the fifth output, denary 5 activates the sixth output, 6 activates the seventh, and 7 activates the eighth. A decoder can be built using combinational logic. This 3 to 8 decoder is constructed from 3 NOT gates and 8 AND gates. Decoders have a number of applications, including selecting a row, also known as a word line, from an array of memory cells based on a binary row address. If the 3 address lines are all at 0 voltage, then only the top row of the array has a high voltage across it. In other words, only the top word line, let's call it word line 0, is asserted. Notice how each of the decoder's inputs is split into two. Then one of each pair is passed through a NOT gate. So the output voltage of each NOT gate is high. Only the top AND gate is connected to the three lines which are high. So only the top AND gate has an output which is high. Now the row address 001 is applied to the inputs, and a different combination of lines inside the decoder are now high. Only the second AND gate down has three inputs which are high, so only the second word line 1, is asserted. This is row address 010, the number 2 in denary. Word line 2 is asserted. This is row address 011, 3 in denary. Word line 3 is asserted. Row address 100, the number 4 in denary, asserts word line 4. Address 101, 5 in denary, asserts word line 5. And address 110, the number 6, asserts word line 6. Finally, row address 111, which is 7 in denary, asserts the bottom word line. A 3 to 8 decoder can be constructed with an extra input whose job is to enable the device. Each AND gate now has 4 inputs instead of 3. Only when the enable input is high does the decoder activate anything at all, according to the selection inputs. Finally, it's worth mentioning that it's possible to combine decoders to make an even larger one. In this example, a pair of 3 to 8 decoders have been combined to make a 4 to 16 decoder. Notice that the NOT gate connecting them together ensures that the enabling input of one decoder is always the inverse of the other, so only one of them will ever produce an output.